So recall we've said this before that lots of the results we love for in the real numbers, especially results for continuous functions, work only in closed bounded subsets of the real numbers. The extreme value theorem, or the result that continuous functions are always uniformly continuous, those work on closed bounded subsets of the real numbers, but not on non-closed or unbounded sets. And it turns out that a lot of them use a little bit of extra structure that the real numbers have, but arbitrary metric spaces do not. You cannot prove the extreme value theorem on an arbitrary closed bounded subset of a metric space. You need a little bit of extra structure. So I'm going to write down the simplest but also the fairly abstract definition of a compact subset of a metric space. We will end up seeing that you can prove the extreme value theorem on compact sets. And then in a little while, we'll be able to write an equivalent condition that's more concrete, more easy to get your hands on, but also, oddly, much harder to work with. So here is definition 5.5.1. So we start with a metric space. And you can define what it means for the metric space XD to be compact, and then you can say that a subset is compact if the subspace KD is compact, or you can define it for subsets in the first place. Your book does the second one, so that's what I'm going to do. So there's two conditions that are going to take a little bit of explaining. So first off, let's say there is a curly G is a set whose elements are themselves sets, a set of open subsets of X. And now, what we don't really like saying a set of sets that's confusing. So for our purposes, a collection is just another word for set, but we will generally use collection for set of sets. So we'll say a collection of sets. Hopefully that will help a little bit. And we're going to require that each G in our collection G is open in the metric space XD and is indeed a subset of X. I realize that I am kind of repeating myself here, but this is a tricky concept, so I want to make sure I'm clear enough. And then the other condition we need is that K is not necessarily an element of G. In fact, it's usually not going to be because compact sets usually aren't open, but K is in the union of all the G's. So we say K is compact whenever you've got what we call an open cover. That is, K is contained in a union of open sets. Then there is a G1 that's a subset of G such that K is still covered by just the sets in G1, and also G1 is finite, where by finite I mean G1 contains finitely many sets. So as promised, that was very abstract, so now we're going to write down an example. Let's let X be the metric space R2, my favorite metric space for drawing, and let's let K be this square. So that's the set of all pairs x1, x2, such that x1 is between 0 and 4, and also x2 is between 0 and 4. And let's let G be the set of all balls of radius 3. And then certainly the union of all G and G the union of all these balls is giving you everything. And then let's have a nice little picture. Here is our square K. And then we can draw 4 balls, all of radius 3. That cover this. So G1, we can take G1 to be the set ball centered at the origin of radius 3, ball centered at the other 3 corners, each of radius 3. So this is a collection of finitely many sets, 4 balls that cover our compact set K. Now, certainly our balls are not at themselves finite. Each of these balls has, of course, infinitely many points in it, but there's only finitely many of the balls. And being compact means if you start with an open cover, you can always do this. You can always find yourself a nice finite subcover. Let's have a couple of examples of things that are not compact. So, for example, the real numbers are not compact. So let's let G be the set of all these open intervals, n-1, n+1, such that n is an integer. And so, of course, we can draw this on the real line. We've got it. If you draw these, it should be pretty clear that they are indeed covering all of the real numbers. Put them together, you get the entire real line. But also notice that we hit each of the integers exactly once, no more. And so there are no subcovers of the reals or the integers inside the reals. So there is no subcover of the integers or the real numbers, however you want to think about it. If you've got a subset, a subcollection, and your subcollection covers the integers, then you've got to have everything in G. So your subcover is not finite. So the integers are not compact. I suppose I should say is not compact because we mean the set that's the set of all integers. That singular thing is not compact. And similarly, the real numbers are not compact. You can use this exact same cover with no finite subcover. Here's another example of a non-compact set. Let's let X be any infinite set. D, the discrete metric. And let's let G be the set of all the singleton sets, all the singleton subsets, all the sets that are 1 point. And I want to emphasize this is not the same thing as X. X is the set of all X such that X is in X. G, our cover, is the set of all one-element sets. They're not the same thing. And notice the ball centered at X of radius 1/2. Under the discrete metric, every point is 1 unit away from all the different points. So the ball of radius 1/2, it only contains the midpoint. So G is a collection of open sets. And G has no finite subcover. It's just like the case we saw before, or if you take any singleton set out of G, then suddenly it isn't covering the point that's in that singleton set anymore, and so it's not a subcover. Now, I said earlier you can define what it means for the subset K of the metric space XD to be compact, or you can talk about what it means for the metric space KD, the subspace, to be compact. And as an exercise, as a homework problem, we can think of it a couple of different ways. So I'm going to phrase this a little differently from how your book does this. So let's let KD be a metric space. And let's suppose that KD is a subspace of, let's call it X delta. There might be a number of different metric spaces that it makes sense to think of K as being a subspace of. So this means that K is a subset of X, and also that the D is the restriction of delta, the distance from K to M in KD and X delta is the same for all Km in our subspace K. Your parent metric space X might have more than one metric on it that matches up with K, but we just care about what it's doing on K. Then K is compact in the bigger metric space if and only if K is compact in itself. So you can go back to your definition and just say an open cover is a collection of open subsets of K such that K is that contains every point of K. And you can talk about definition 5.5.1 with K and X being the same set. Here's a proposition that is not explicitly written in your book, but I think it makes all of our examples and a lot of our proofs a lot easier. Let's let XD be a metric space and K a compact subset. Then let's suppose we've got a sequence it's a sequence of sets. So each GJ is a subset of X. Each GJ is open, and it's an increasing sequence. And if this sequence, which you can think of as a collection, is a cover, then K is in fact in one of them in particular. And the proof of this is not hard. We're going to let G be our collection. That's the set of all GJs such that J is a natural number. G is, by definition, it's a collection of open subsets of X, and it's a cover of K. K is contained in the union of all the J's in G. So there is a finite subcover. But since G1 is a subset of G, so we can write G1 to be GJ1, GJ2, up through GJN. So it's finitely many of these sets we started with. And then you just let capital J be whichever of the GJ's is biggest. J1, J2, Jn. Then G sub J sub K, proliferating subscripts. JK is less than or equal to our capital J for 1 less than or equal to K less than or equal to N. So G sub J sub K is a subset of GJ because it's an increasing sequence. So K is contained in the union. And then if you would make them bigger, K isn't certainly going to stop being in the union, and then you can union as many copies of a set with itself as you want, and you'll just get the same set back. So that completes the proof. So now let's start proving some properties of compact spaces, and eventually we'll build up some properties that are strong enough to require compactness. So here is our first proposition. I'm going to break up some of the big multi-part propositions in your book into pieces. Let's let XD be a metric space. And K a compact subset. Then K is bounded. And to prove it, let's let X naught be a point in X. I suppose perhaps I should specify that X is a non-empty metric space, but if X is the empty set, then K is the empty set, and the empty set is obviously bounded, so we'll just assume that X naught is non-empty. Let's let G sub J be the ball centered at X naught of radius J. Then I claim that the GJs satisfy the property we saw before. Then each GJ is open. That's by an example we saw in section 5.3. And clearly these are an increasing sequence. GJ is the set of all points where the distance to X naught is less than J. GJ plus 1 is the set of all points where the distance is less than J plus 1. And if your distance is less than J, then certainly your distance is going to be less than j plus 1. So we need to check that the union of the GJs covers k, but in fact it covers x. If we've got a point y in k, which is therefore a point in x, then the distance from x to y is a real number. So by the Archimedean property, there's a natural number which is bigger than the distance from x to y. So y is in the ball centered at x naught of radius j, which is gj. So k is contained in the union of all the GJs. So by our proposition, k is contained in the ball centered at x naught of radius j for some positive number j, positive finite number j. So by one of the last propositions in section 5.3, k is bounded, meaning it has finite diameter. Next, we're going to see that compact sets are always closed. This is part 2 of proposition 5.5.2, part A. So let X be a metric space. And then if K is compact, then K is closed. Another fairly simple proof. We're going to start with a sequence of points in K that converges to a point in X. And all we need to show is that K contains this point X. Let's let G sub J be everything except the closed ball centered at X of radius 1 over J. So since closed balls are indeed closed, that was example 5.3.4. We have that GJ is open by the definition of open set at the start of section 5.3.1. And then clearly these are increasing sets. That is, as J gets bigger, your radius 1 over J gets smaller, so your closed ball gets smaller. Now, so if the union of the GJs contained all of K, there would be a finite subcover, then one of the GJs would contain all of K. Fix a J. Since 1 over J is bigger than 0, there is a natural number n such that since xn is going to x, at least one point, infinitely many of them, but at least one of them has to be within 1 over j of the limit. So xn is not in gj. So since we started out with a sequence of points in K, K is not a subset of GJ for any J. And now by our proposition, if K is contained in a union of an increasing sequence of open sets, then it's got to be in one of them in particular, and it's not in one of them in particular. So K is not contained in the union from J equals 1 to infinity of GJ. But if Y is in X, and y is not equal to x, then the distance from x to y is greater than 1 over j for some j. So this union it's got to be all points except your target point. And maybe I'd better draw a picture. Here is our space X. Here is our target point X. We've got our sequence of points heading towards X. And then our GJs are you take succeedingly smaller and smaller balls around your point X. And your GJ is everything outside of those balls. So as your balls get smaller and smaller and smaller, you exclude everything except our one target point. Little x here in the middle. So put it all together. K is a subset of X. K is not a subset of X minus this 1 point. So the only way that could happen is if there's some point in K that's not in X minus X. The only way this can happen is if little x is in K. So K is closed. Next, we're going to show that closed subsets of compact sets are compact. There are lots of closed sets that are not compact. For example, all the real numbers are closed as a subset of the real numbers. But if you're closed and you're contained in a compact set, then you must yourself be compact. So we've got our metric space, we've got our two subsets. F is a subset of K is a subset of X. F is closed in X, and K is compact, meaning that K is also closed, among other things. Then F is compact. And we can write out a very direct proof. Let's let G be an open cover of F. So that means that F is a subset of the union of all the open sets in G. And if G is in our cover, then G is an open subset of X. Let's let, I will call it H. It's going to be G union with the collection. It's a one-element collection, but I don't want to call it a set. We're going to take X and we'll delete F from it. And then we have that if G is in our new collection, then either G is in our old collection of H, so it's an open subset of X, or it's the new set we threw in X minus F. F is closed, so X minus F is open, so in either case, G is open. And X, that's F union X minus F. That's a subset of our open cover of F. Let's put some parentheses around that. And then we throw in X minus F. That's exactly the union of all the things in our new collection. And since K is a subset of X, we have that our new collection H is an open cover of K. So there is a finite collection subset of H1 subset of H with K contained in the union of all the open sets in our new collection. And then we just let G1 be H1 intersect G. That's the set of all G in H. So we are probably deleting throwing away the set X minus F. It might have been in our first open cover, but probably is not. G1 is a subset of G. G1 is finite because it is a subcollection of H1. And F is contained in K, which is contained in the union of all G in G. You take everything in G1 and you throw in X And maybe you have to throw in X minus F, maybe you don't. In any case, K is contained in this set. So every point in F has to be in either X minus F, wait, that can't happen, or this other thing that is the union of the G and G ones. The first one can't happen, so F has an open cover. So we've seen that every open cover of F has a finite subcover G1, so F is compact.